So now I want to talk about Transgcn, which is another algorithm for knowledge graph embedding. So like TransE, it is for embedding uses translation idea that, for example, heads and relations, if you sum that, should be close. It should be close to the tail. So heads plus relations should be. But now the idea is that we want to add convolutional graph convolutional network and take advantage of those graph neural networks. So this is a really good article to see different paradigms for knowledge graph embeddings, especially for link prediction, which is really an important problem. So here there are many ideas. Some of them, like the previous lecture, was based on translation distance. Of course, there are other paradigms like rotation. You work on complex plane, so you have real and imaginary of a point. And so, for example, for subject, you have some object around that. But last lecture, I talked about translation distance only. So, of course, there are other paradigms as well. But if you want to use neural networks, like graph neural networks, in this lecture, I'm explaining Transgcn, Transgraph Convolutional Network. And this is the idea. This is the article, again by these nice researchers. And so coupling transformation assumptions with graph convolutional networks for link prediction. So first I should explain graph convolutional networks. Of course, I have a playlist for graph neural networks. I explained graph attention. Now I'm explaining graph convolutional networks. So there are two major approaches to deal with that. One of them is spectral based method. The other one is a spatial based method. And there are applications of GCN to computer vision, NLP, which is my favorite, and science, for example, chemistry, and social networks and physics. So what is this graph convolutional networks? In 2017, they created this approach for example, if you have a filter, because they want to generalize convolutions. So you have a filter and then convolve it with a signal, you get this. But it is hard to compute. So, the spectral graph convolution is like this, but it is computational expensive. That's why they use Chebyshev polynomial. I've used Chebyshev polynomials in Markov chain theory. If you watch my playlist on Markov chains, I explain how you use Chebyshev polynomial there. And here, it is another application of Chebyshev polynomials. And so you truncate it and you can use it. So if you use this is a simple proof of that you can finally approximate it like this. And there are k parameters. So you can say that by stacking multiple convolutional layers of this form, you can work and you have a good neural networks. But that's not easy, because by doing that you are encouraging overfitting. That's why these people introduce this approximation, which is a linear formulation of that, and finally, and then using this approximation, they hope that they can avoid overfitting. And so, like any other graph neural networks, you first embed it, and then you use the loss to find those weights that you have to design for your graph neural networks. So, for example, for node classification, for any classification, it's traditional to use cross entropy loss. And so this is the graph convolutional neural networks. Now, what is Transgcn? We want to, as I said, embed the knowledge graph. So they use this article and they call it RGCN method. So the article 2019 is inspired by this article in 2017. So they want to use graph convolutional neural networks, but in RGCN, they don't learn relational embeddings, and thereby you have to do something. So I will explain this article 2019 in a second, and like any other aggregation, we call it aggregation because sometimes your weights are easier, sometimes like this, but here I want to show you that there are some ideas for defining a good loss in knowledge graph embedding. The easiest one, like the previous lecture, which was Trans-E, was based on translation-based methods. But there are other paradigms as well. As I said, rotation and other paradigms like semantic matching energy-based methods. And also, rotation is here. So this idea is very nice as well. And so the idea behind Transgcn is that similar to RGCN, aggregated structural information and self-loop are combined for entity embedding updates. So we update those embeddings, and this is the law. First, we should, we have now two things. It's not just the nodes, not just these entities that we should update. We should also update the relations. So it adds the complexity to all these knowledge graph embeddings. And, there is a article for message passing neural networks, but here we use message passing phase for nodes. We don't want to read out phase for the whole graph, and so this is the idea of message passing. And then because there are some incoming messages, for example, there are tau in, there are incoming messages, so we separate them so that we do not confuse them, and there is no, there is just, here I will explain why. So tau in is just all the triples, head, relation, tail, and sometimes you need to, sometimes your relationship is different. So you should know, the direction of that. So we divide them into in and out. So this is just for, respecting this relationship. And you see this in here. It is here. So here, when you say star, it's for out. When you see this one, it is for in. So it's nothing special to talk about. But the score function is inspired again by that Trans-E article, which had many citations. And so this is the score function. And it's a translation-based method. This is the embedding for heads and then relation, and this is for tail. And we want to minimize this. Again, we are using this margin, which I don't like because it's parametric. So we have some other paradigms in order to deal with this problem, which I really like to use mutual information. Maybe I should write an article about it, or you should write an article about it sooner than me. So just like the article that I explained, mutual information for semantic hashing, you could use it in order to avoid this problem of gamma, which is just a margin that you should be very clever to choose. So it's a parametric this gamma makes it a parametric approach. And Of course, it's a conjecture that some people say that if somebody has a high IQ, he or she may have low EQ. But maybe you are an exception. You have high IQ and high EQ. Of course, it is always good to have a trade-off. So it's a distribution. It's a uniform distribution. I go for a uniform distribution.